Hello everyone, welcome to another video. In this video, we'll discuss the centripetal force and its origin. So before we dive in, let's define what velocity means. Velocity means change in displacement. It's the rate of change in displacement, which means rate of change in displacement over time. And displacement is distance moved in a particular direction. So if either the speed changes or your direction changes, your velocity changes. The speed changes because speed is essentially just the magnitude of velocity. So you can really write speed as magnitude of velocity. So when the object is spinning in circles, its direction changes continuously, but its speed doesn't change. And how can that happen? Well, in circular motion, the acceleration is not really in the same direction as velocity. It's actually perpendicular to it. So if you just look at this figure, you can see that velocity is vertically upwards here, and it's at an angle at this position, which means its magnitude remained constant, but its direction changed. So in a sense, this object is accelerating. Now, in circular motion, acceleration is perpendicular to velocity. So an object has a constant velocity in this direction, and it has an acceleration perpendicular to velocity, which is vertically downwards. So doesn't that mean this object is going to fall? In fact, it does. And that's why we have this projectile motion where if you throw an object, it's going to follow a parabolic path to the ground. And the reason circular motion occurs is because an object is continuously falling. But it's falling in such a speed or in such a way that its path matches the curvature of the Earth. Now, this is something you've probably heard somewhere, but in picture, this is what it looks like. So let's consider a satellite spinning, and during its spin, it's falling. But because its speed in this direction, is high, it kind of, because its speed in that direction is high, it falls at the same rate as the Earth. If you just carefully look at this orbit, it technically fell from its original position. And this satellite fell at the exact same rate, so it really caught up to this orbit. And really, if you want to see how what the idea of Earth falling, if you just look at this picture, which is highly exaggerated, you can see that this is the horizontal line that you're standing on. And because of the curvature of the Earth, you can really think of it as the Earth falling underneath you. Now, this is a weird concept, but really, once you get the hang of it, it becomes really easier to apply to other ideas. So, the object continuously spins in circle. In our case, it's the satellite. So, how do we know how its velocity is changing? In this case, not speed, but the angle, or its acceleration in terms of the angle that it covers, or acceleration in terms of change in directions, right? That's the idea that I wanted to convey. So the value of acceleration is going to be acceleration equals v squared by r. Now there is a derivation towards this, which I would link in the description below. Feel free to check it out whenever you like. So the centripetal acceleration is given by v squared by r. Force equals mass into acceleration. So really, centripetal force is going to be mv squared by r, where m is the mass of the object that is spinning. So let's consider this scenario where you have an object of 5 kilograms spinning at 4 meters per second and divided in a radius of 4 meters, and that requires 20 Newton. So what it means is for an object of 5 kilogram to spin at 4 meters per second in a radius in a circular path of radius 4 meters, you would require to provide 20 Newton force in order to keep it in its path. Okay, so you might think of it as a different force because that's a misconception that happens quite regularly. So if you might like to think of it as a separate force, but it essentially isn't. It's just a fancy name given to any force towards center. Well, that actually causes a circular motion. So in our case of satellite, that centripetal force is provided by gravity of the Earth. So really, let's consider. Let's find out some relation between the gravity and the circular motion of the satellite. So gravity, from the previous videos, gravity is going to. So actually, let's solve it in a step by step, as we would normally do when trying to figure out the relations. So we know that force of gravity. Sorry, let's change that. We know that force of gravity provides centripetal force. So Fg represents force of gravity, and Fc represents centripetal force. So gravity provides the centripetal force. Centripetal force is mv squared by r, and Fg is gmm by r squared. So if we just do some arithmetic, v squared equals gm by r. So what this shows, this formula or this idea gives you what velocity would be needed in order to orbit at a specific distance from a mass. And that gives you a pretty good insight on what speed a satellite should rotate or spin around the Earth in order to stay in orbit. Now, let's consider a few more examples. Let's consider a few more examples. And that's going to be a car on a banked road. Sorry for the diagram, poorly drawn diagram. So instead of a car, let's just put a block. That really represents a car, but it really, the principle applies in the same way. So you have the weight of the car or of the block acting vertically downwards. You have the contact force perpendicular to the surface. So contact force is always going to be perpendicular to the surface. So this is it's always given as r. And now a component of the contact force, let's consider this theta, is going to balance the weight of the car. That means there is a horizontal component of the contact force, which is r sine theta. So that means this horizontal component is centripetal force. So you can write Fc equals r sine theta. And here we are considering that friction is negligible, so this really simplifies it. But in a real scenario, if there is a banked road, both friction as well as the contact force provides the centripetal force. Okay. So let's move on to a more complicated scenario. Let's say a plane going in circles. Okay. So you might have seen multiple times of planes really making a turn. Okay, so really if we consider a simplified model of a plane that I'm just going to represent by a box. Okay, so a plane flies because of this force called a lift is this force called a lift, which acts perpendicular to the plane of the plane. That's a weird phrasing. Which acts perpendicular to the wings, basically. And weight is acting directly downwards. So when the plane makes a turn, it actually tilts slightly. And note that lift is dependent on speed. So if the speed of the plane increases, its lift is going to increase. But we can discuss it in a later video. So what happens when a plane decides to make a turn is that it tilts slightly. And that makes the lift force at an angle. And the weight still continues to act perpendicularly downwards. So that means a component of the lift force is balancing it. Not the lift force directly, but a component of lift force is preventing the plane from falling. That means there must be a horizontal component of it. The vertical component is balancing the weight. That means the horizontal component is going to provide the centripetal force. The physics behind it is really simple, but it has huge implications everywhere. So really getting an understanding of these simple things can make learning these mega structures and all of these engineering marvels much more interesting. So I hope to see you in the next video, and